Good. All right. So I've decided to do something kind of a little bit weird this year because one needs to do that sort of thing if one has taught at machine learning summer schools for a long time. So usually what I would do is I would start with very basic fundamental stuff and build up, and then towards the end I would give kind of like what I think are the most exciting research directions in my own research program and so on. Okay, and what I've done is I've flipped it this year. So I'm going to start with, what I'm really excited about, and then hopefully you'll be motivated tomorrow to kind of come to the lectures where I'll explain some of the jargon and terminology that I'll talk about today. So I flipped it around. But the first thing I want to say is it's hard to imagine a more exciting field and an exciting time to be in. So it's a crazy time to be a machine learning researcher. For many of us who've been around for a few decades, like Bernard and I, as researchers in the field, when we started out, it was very much just the kind of academic passion, sort of purely intellectual endeavor where we like math and we like computers and we think we can come up with some better ways of getting computers to learn from data, and we don't really think it's useful, but it was really interesting, certainly. So things have just changed dramatically, and the reason they've changed is that there are just so many incredible applications of machine learning out there, and you all don't need to be told this because you are very heavily interested in doing research in machine learning. But areas like speech and language have been completely revolutionized by machine learning methods. Computer vision, even areas like scientific data analysis. We have, in the sciences, we have very high throughput methods that allow us to collect vast data sets, and we need computers to help us understand the data. We're all familiar with recommender systems. There's a lot of excitement around self-driving cars, and areas like finance that have flirted with machine learning are now really starting to take it very seriously. So this is just 6 I could fit on one slide. I could have put a lot more on there. So it's an incredibly exciting time to be doing machine learning. It is actually really useful. It feels like a bubble, but it's, it also is useful to a lot of people. There's reasons why they spend lots of money on this stuff. Other examples that are very familiar now, these breakthroughs, for example, by DeepMind in being able to play Atari games at superhuman level, at least sort of a majority of the games at superhuman level. Very impressive breakthroughs in reinforcement learning combined with some deep learning. Again, similarly, in the game of Go, which I certainly thought a few years ago was 10 years away. Less than 10 years ago, I thought it was 10 years away. And the whole community was pretty stunned when the breakthroughs happened this year, again, by our neighbors at DeepMind. How many people know what this is? Raise your hand if you know what this is. Not that many people. Brains are a set of human experts, and Libratus is a computer. And the numbers in brackets are negative numbers. Okay, so this is from a CMU team that had this breakthrough earlier in the year playing poker. And poker is a particularly interesting game, so Libratus was beating all these human experts massively. Poker is a particularly interesting game because, unlike Go, the state is unknown, right, in the sense that when you're playing poker, you don't know the hands of other people. You have to infer things from missing information, and all sorts of other things. Is kind of, people think of it as a psychological game, right? You have to be able to bluff, right? So, what happens with computer trust and transparency if you're actually training your computer algorithm to be really good at bluffing, etc. And so, of course, you have to do that to win at poker. So again, a really interesting breakthrough. In this particular case, it wasn't really deep learning. It was more kind of game theory combined with sort of traditional AI methods and some reinforcement learning. Although there's another team in Alberta that also has a similar breakthrough where they might have used deep learning as well. So in the field of machine learning, you know, it's kind of bewildering, right? There's so many different methods and many links between the methods, many terms that are thrown around, different camps. You know, some people feel like they fall in one camp, and some people feel like they fall in another camp, and then you have, you know, statisticians maybe who don't really understand what this stuff is and what's the big deal. Well, no, actually it goes like this. Usually they don't understand what the stuff is, so I've had many very senior statisticians come up to me and say, "What's deep learning?" And then after explaining to them, which takes about 2 minutes, they're like, "Oh, is that it?" And then they go back to not being interested. Right. So, you know, there are definitely, you know, just a lot of communities, a lot of terms out there. You know, you'll get lectures on almost all this stuff, I think, which is great in these 2 weeks. I'm working mostly in probabilistic modeling and Bayesian methods. This is the area that I've been most heavily involved in. I actually started out doing neural nets, but I shorted my neural net stock very early, as they say. I thought, oh, this stuff is not really interesting. I'll do something actually interesting at the very wrong time to do that. But I'm desperately looking for a copy of my undergraduate thesis because it was on, and I don't have it, unfortunately. I have a draft with some grades on it, which I don't want to share. But the undergraduate thesis that I wrote in 1990 was on neural networks for parsing natural language. So I was actually training recurrent neural networks for parsing natural language. Back then, it was very difficult to do it on a CPU, so I had to use a connection machine, which was cool. It's this big block with lots of lights in it. A lot more cool than GPUs, but a lot slower and much more expensive. And it didn't work at all, basically, because my data sets were tiny. In fact, you know, they're pretty laughable, and it was crazy to think that it would even work. So I'm going to spend a little bit of time talking about neural networks because it's the big elephant in the room, and then I will switch gears and talk about probabilistic modeling. So neural networks and deep learning, you've already had a few lectures about this, are hugely exciting, right? So again, what is my 2-minute explanation that I would give to a statistician of what a neural network is? Of course, there are many different variations on neural networks, but let's just focus on a network that is used for supervised learning. So it's just mapping from some inputs to some outputs. So what are neural networks? Neural networks are tunable nonlinear functions with many parameters. Okay? And the parameters, which I tend to call parameters theta throughout my lecture, the parameters are the weights of the neural network. The neural network is a model. It's a model of the outputs given the inputs, parameterized by the parameters. And interestingly, unlike many other things that have been around, it's both nonlinear in theta and in x. Okay, so it's a nonlinear function both of the parameters and of the inputs. And here is possibly the simplest neural network, which has been around for 60 years or so. And that is basically if you take a linear combination of the x's and then you pass it through a nonlinearity, like a sigmoid, logistic, or probit, then that could be interpreted as the probability of some binary class label given the input. That simple neural network is logistic regression. If you use a logit nonlinearity or logistic nonlinearity, logistic regression obviously has been around for many, many decades. And actually, a lot of what people tried was just stacking lots of logistic regressions together to go from X to Y. So this is kind of the simplest neural network. This is not a very deep one, right? And a deeper neural network or a multi-layer neural network, essentially what it does is it models the overall function as a composition of functions, which are these layers. So I'm going to go from the input to the output by composing multiple nonlinear functions, vector functions, to go to the output. So this is now a two-layer neural network with a linear output, some Gaussian noise or something like that. Okay? And so usually these things are trained to maximize likelihood or penalize likelihood. People talk about error functions that they're minimizing, but actually almost all error functions used in practice correspond to the log of the likelihood. Yes? That's a very good question. In fact, have you had lectures on support vector machines yet? So the hinge loss, for example, is often used in maximum margin support vector machine models and things like that. Losses like that don't correspond to likelihoods because they don't sum to 1. And if you exponentiate them and you take the possible outcomes, they don't sum to 1. So that's why they don't correspond to likelihoods. But almost every other loss that people actually use in practice corresponds to a likelihood. So it's actually a neural network is a probabilistic model. It's just a probabilistic model of y given x. And how are they trained? Well, they're trained using generally some variant of stochastic gradient descent optimization, which is sort of like the simplest optimization method you might learn in an optimization class. And then people say, oh, but you clearly would never want to do that. And then they teach you lots more complicated stuff. But it turns out that actually it's a pretty good method when you deal with very large data sets. So neural networks are nonlinear functions with a little bit of basic statistics, like likelihoods, and a little bit of basic optimization, like stochastic gradient descent. Okay. As I said, some of us were really excited about this in the 80s and 90s. That's really what got me into the field. Some of the models that we have now are actually not that different, technically, from things that people were experimenting with in the 80s and 90s. So what's changed? Why is there this sort of revolution now, which we certainly didn't have in the 80s and 90s? And I would argue that there are sort of 5 points here. So one of them is there have been some new ideas. Well, this is good. You know, in 30 years, you would hope that there would be some good ideas coming out. There are algorithmic and architectural innovations. People did try deep networks back then. Deep meant like 2 or 3 layers, but it just was difficult to train. And then over time, people have figured out that actually, if you want to use multiple layers, there are particular activations like rectified linears that work better when you have multiple layers than, for example, the sigmoids that everybody was using. It was a bit of a trial and error. People stumbled into something that works better. There are some better methods to regularize. For example, dropout still seems a good one. And there are other architectural ideas like LSTMs, which essentially, again, involve trying to come up with an architecture where if you have many layers or long-term dependencies in time, which is basically mathematically equivalent to having lots of layers, then both in the forward pass and in the backward gradient computations, information doesn't go unstable, basically. The pass doesn't become unstable because that would cause you not to be able to learn with multiple layers. So ideas like that, and this is a short list. One could come up with a much, much longer list of innovations. So that's first point, new ideas. But importantly, we have vastly larger data sets. And that's thanks to the web, basically, right? And, you know, so now if we're doing computer vision, we can actually run it on, you know, literally hundreds of millions of images. Same for speech and other areas of sort of pattern recognition. It doesn't mean that in all applications we're going to have vast data sets. So we need to be careful about that. Because data comes from the real world, and sometimes, you know, it's actually not possible to get 100 million examples. Certainly not labeled examples. Also, well, going along with that, we have vastly larger compute resources. We need those to be able to process the vast data sets. So we have GPUs, now maybe TPUs, other architectures coming out in the cloud, etc. We also have much better software tools. We have, again, just a partial list in case your favorite one isn't there. We have software tools that mean that essentially what you need is you kind of need a high school education and some good programming skills. And you read somebody's blog, you take the software, and then you have something that actually does, you know, computer vision. And it's incredible. It's amazing. You don't even have to know what a derivative is, let alone actually compute the derivative. Okay? This is great. It's also a little bit dangerous. But I think on the whole, it's great in the sense that we can make lots of progress. And finally, because of all these things, there's been incredible industry investment because it's proven to be useful, and there's been a lot of media hype, and that feeds on each other. More people come into the field, more stuff appears to happen because more people have come into the field, and it sort of creates this virtuous cycle. So this is awesome. It's very exciting. You know, I'm certainly surprised at how quickly it's been going. But we shouldn't lose sight of the fact that there are some limitations to deep learning. So these neural networks and deep learning systems give amazing performance on a lot of these benchmark tasks, but they're generally, first of all, very data hungry. They often need, you know, hundreds of thousands or millions of examples. They're very compute intensive to train and deploy. So, you know, if you have a cloud available to you, then that's great, but if not, it might be a little bit harder. They're quite poor at representing uncertainty, and I'll talk about this a lot more later on in the talk. So, although basically all neural networks are probabilistic models of the output given the input, if we take the predicted probabilities on the output side, we can't really trust them. And one of the examples of a way in which we can't really trust them is that they're easily fooled by adversarial examples. So how many people know what I mean by adversarial examples? Raise your hand if you know. Almost everybody. So these are examples that are either imperceptibly different from other examples, but for which the neural network will confidently give you the wrong answer. And what I worry about is not the fact that it gives you the wrong answer. It's okay to make mistakes. It's not okay to confidently make mistakes. That's what bothers me in a student or in a neural network. Okay. And there are other forms of adversarial examples which are not, they're not that they're imperceptibly different from a normal example, but they're just very obviously different from any normal example, just weird patterns for which the neural network will very confidently give you the wrong answer. Okay, or an answer. Any answer is wrong because these images, these are in particular for images, these images are nonsense images, basically. Neural nets and deep learning methods are generally finicky to optimize, although we're getting much better at these things. And that means that they require expert knowledge and experimentation to get right. And also for a lot of real-world applications, it's very problematic that they're generally uninterpretable black boxes. They're lacking in transparency. They're difficult to trust. If something goes wrong, we don't know why it went wrong because we have 100 million parameters, and it was sort of like the decision was made by the 100 million parameters. And this is actually pretty important because, for example, things do go wrong. Like if you're building a car that has a pedestrian there, you really don't want it to go wrong, right? And if it does, you need to understand why it went wrong, and you need to be able to fix that. Or if there is a GDPR. Has anybody heard of GDPR? The EU's General Data Protection Regulation, which is a law that's going into effect, which basically says any algorithm that makes a decision, the human affected by that decision has the right to an explanation. So if you go to a bank and the bank, declines you a loan, then you have the right to say, well, why did you decline me the loan? Was it because of where I live, or my race, or my age, or what? Why was it? Because maybe it's illegal what the bank did. And that's certainly a problem if your method is a big black box. Okay. So they're great, but there are limitations. And, there are many people who know about these. There are many people who are doing research on these things to sort of overcome these limitations. So let's go beyond deep learning, and let's talk about kind of maybe a different way of thinking about machine learning. This is sort of where I'm going to start talking about probabilistic models and Bayesian methods. This is maybe a little bit of a caricature, but I think that there are kind of two ways that people approach the field of machine learning. One of them is there are a whole bunch of tools that we have to learn. It's like a big toolkit, and we've got to learn all of these different tools because they do different things. These tools process data in particular ways. They're tunable, and we can compose the tools together to process data in various other ways. Okay? So this is the toolbox approach, and it can work extremely well. So there's nothing really wrong with this approach. The other way of doing things is thinking about, like, what does it mean to learn from data? Kind of like, is there like an underlying mathematical theory for all of this stuff? Is there a science of learning models from data? And the emphasis here is not just tools for processing data. A data processing tool isn't a model. It just takes inputs and it produces outputs. The emphasis here is on building models. So what do I mean by building models? And this is what I'm going to emphasize now. And of course, you've had some, I know you've had some overlapping material. You've probably heard Max just today talking about similar ideas. So what do I mean by building models? Well, the concept of a model isn't just something specific to machine learning. In fact, the concept of a model is fundamental to all of science. Right? Science isn't about collecting data or butterflies or something like that. Science is about understanding the world, right? And well, what do people use to understand data? Well, they use models, and models, I would say, one way of thinking about a model is a description of data that one could observe from a system, okay? There are other reasons a model might be a good model, like maybe it's intuitive to a human being. Maybe it provides some sort of explanation or something like that. Those are a little bit more difficult to quantify. But one very quantifiable thing a model can do is make predictions about potential data, right? And that's actually a really good way of telling whether your model is good or not. So if you want to say, well, is Newton's model of physics better than Einstein's model of physics? Well, then there has to be some experiment, some potential data where the two models disagree, and then you can evaluate which one fits the data better. And that's essentially how science progresses. And we're going to think of machine learning in terms of building models of data. And one of the things about models is they're fundamentally tied to the notion of uncertainty. Because there are only two, from a Bayesian point of view, there are only two things out there in the world. There is data, which is measured and observed, and then there is everything else. And everything else, one can't be certain of because it wasn't measured or observed. Okay, so we need to be able to represent our uncertainty about everything that's not data. So what we're going to do is we're going to use the mathematics of probability theory to express all forms of uncertainty, including things that we sometimes call noise and so on, about our model and about, everything that we can measure. And the reason we're using probability theory is in the same way that, calculus is the mathematics of rates of change. Probability theory is the mathematics of uncertainty. So there is kind of like, we have no real other choice. Some people might argue, you could use this or you could use that, but I don't. And essentially is SGD with some noise added carefully, okay? And the interesting thing is it can be derived from the theory of Markov chain Monte Carlo methods with a few approximations. Algorithmically, it's just running SGD with a bit of noise added. Okay, but conceptually, when you do that, you jump from targeting a point to targeting the distribution. So now you can interpret the output of that as an approximation to the full distribution, and then the only problem you have at that point is not a computational problem because the algorithm runs in the same computation time as the other algorithm. Basically, adding noise is not very expensive, right? It's a memory problem that, in theory, you should be storing lots of parameters to make predictions because you want to be, averaging over parameters. So basically what you should be doing is storing a bunch of parameters along your your SGLD run, and then if you want to make a prediction, you average over those parameters. Okay. So these two worlds are not so different. It could come down to just adding noise to your favorite optimization algorithm in the most extreme case. The other way they're interesting is, for example, variational Bayes is taking an approximate integration problem and turning it into an optimization problem. So remember, optimization and the people who do this are doing approximate integration. Okay? But variational methods turn an approximate integration problem into an optimization problem. And then stochastic variational inference basically takes that and does, stochastic optimization of that with many batches. So you're hybridizing ideas across the two areas very quickly. But I want to be clear that Bayesian belongs in the algorithms column, not in the models category. It's a class of algorithms. I mean, it's not a single algorithm, but it's sort of like algorithms that target this. So you can apply it to any well-defined model. And for example, if you take the case of neural networks and deep learning, and you break out of the point estimation view, and you say, well, what would it take to do Bayesian inference over the parameters? Well, that's an idea that's been around at least since the 90s. I mean, there was a whole workshop on this at NIPS, which was really fun, and actually gave a talk on the history of this stuff. And it goes even further back than it goes to the 80s. Even Jan LeCun was involved in one of the early papers, although he didn't realize it, that was doing Bayesian inference in neural networks. Okay. And then the heyday came in the early 90s with people like David Mackay and Raffer Neal and Jeff Hinton, and the work has been continuing. And the reason we should care about that is not what happens when we're making predictions where we have a lot of data. So this is, imagine a neural network that's fitting a function, inputs and outputs, x's and y's. So when we have a lot of data, any sensible method is going to do fine. Okay, you know how many layers you have and so on is not going to make a big difference. You can change your activation function, maybe if optimized, it's not going to make a difference. When you go to extrapolate, when you go outside of the range of your data, then that's where it might actually be really helpful to have represented the fact that you were not sure about those parameters, that you were uncertain about those parameters. And so you should be considering many different extrapolations and averaging across those many different extrapolations. Okay? So that's where that's one particular place where this sort of marriage of Bayesian methods and deep learning is helpful and can give you something useful. Any questions? I'm happy to take questions. I have another half hour to go, I think. Hopefully there's still beer out there. And posters, of course. Okay, so when do we need probabilities? Well, I would think that you need probabilities for aspects of learning and intelligence that depend crucially on representing uncertainty. That sort of makes sense now, I think. And well, now what requires uncertainty? Well, think about forecasting problems. Almost every forecasting problem, forecast seems quite useless to me unless it has some measure of uncertainty, right? Decision-making problems often depend on uncertainty because you want to make a decision for which the consequence of that decision into the future is as good as possible. And of course, we have to be uncertain about what the possible futures are because the world isn't deterministic. And so we need that uncertainty to be able to figure out whether a decision is a good decision or not. So almost all of the deep RL work, when you look at it closely, they really are going out of their way to try to represent uncertainty in the future outcomes of decisions. When you're learning from limited, noisy, or missing data. So, we're very comfortable with the kind of ImageNet paradigm where we might have a huge number of labeled images. But now if you think about applying machine learning methods to medical applications, where you might have many patients, but for each patient you might have a very small amount of medical tests or information about that patient. And there's a lot of missingness, and there's probably noise in those tests, etc. And it's not okay to get things right on average. Every patient cares about the fact that you want to get things right on that patient, right? So we probably want to be able to represent our uncertainty in the data there. And that's sort of related to personalized models, like personalized medicine or personalized recommendations. Again, you might have a lot of clients or, customers, but you might have very little data on each one of them. The whole field of data compression is about probabilistic modeling. Basically, every lossless compression algorithm out there is implicitly or explicitly representing a probability distribution. So if you want to build a better data compressor for any kind of data that you have, essentially what you're doing is building a better probabilistic model. And the last thing here is something that I'm particularly interested in, which is using the representation of uncertainty to automate modeling, discovery, and experiment design. And so, I'm obviously doing this role at Uber right now as chief scientist at Uber, and it's actually really interesting because well, apart from the fact that every day I've gotten into the habit of checking the news to see if there's another piece of news. So our CEO just resigned, in case you missed it. That was today's news. Little things happen every day, not a big deal. Yeah, just little things happen every day. So it's certainly been a very exciting time for me. But scientifically, it's really, really interesting because I've spent, over 20 years as an academic doing machine learning, and now what I've gotten to see in the last 6 months is the incredible range of applications of every branch of machine learning in a very large technology company. Okay, so I feel like almost everything I've learned in machine learning is now useful in some way or other for some different aspect of a company like Uber. So why is that? And why can't we just hire a couple of high school students who don't know calculus but can program in Python and run scripts in Torch or whatever, PyTorch? Well, we can't do that because not all the problems map onto deep learning problems. We certainly use deep learning for like a lot of our perceptual problems, but a lot of the problems that we actually have are things that involve modeling. So understanding cities, understanding supply and demand of drivers and riders, modeling that, predicting, forecasting that into the future. So spatiotemporal models. ETA prediction, so understanding how long it will take to get from A to B at different times of day under different circumstances. There's something called Uber Eats where you order food. We actually have to build models of how long is it going to take that restaurant to make that meal, okay? Because actually if we do that, then the driver shows up when the meal is ready and doesn't have to wait there 20 minutes, and then the customer actually gets their food that much more quickly, basically. In the pricing models, in business intelligence, modeling traffic, and just understanding cities in general, we have a mapping team. And I haven't even talked about self-driving cars. It's all over the self-driving cars framework. So we're not just doing perception. Of course, the self-driving cars work needs a lot of perception for which we can use deep learning. The self-driving cars also need to be able to model and forecast what's going to happen with the different kinds of objects, the cars, bicycles, pedestrians, etc., until a few seconds into the future. So that's about probabilistic modeling and forecasting as well. Like I said, almost everything involves some aspect of learning and decision-making using uncertainty. So it's great. I mean, it really is actually very interesting. And of course, we are also doing flying cars. Well, I've been told not to call them flying cars. The guy who runs this hates the term flying cars. They're vertical takeoff and landing urban aviation vehicles. But come on, flying cars just sounds more interesting, right? And, you know, the interesting thing about this company is, first of all, it's made some bad mistakes. But it's very good at change. So it's very good at embracing change, and you know, I think that's reflecting itself, and it's fearless about action. So basically, when Uber decided that actually vertical takeoff and landing urban aviation was really important to the mission of building, you know, the future of transportation, it committed to having trials by 2020. 2020 is pretty soon. So 2020 in Dubai and Dallas, we've committed to having trials of passengers flying into cities. So we'll see. Should be interesting. Okay. So that's it for Uber. Let's talk about this sort of big vision. So this is actually, I got asked to give a talk once, and they said, could you describe your research program in one slide, please? And that was a great exercise because I had to do that. And so this is the slide that describes everything that gets glued together, what I'm passionate about, and kind of a lot of the themes that I talked about tie into this. And as I said before, I'm kind of flipping these lectures. I'm sort of now going to talk a little bit about the stuff that we do in our group and why we do it and why I think it's important. There'll be a lot of tutorial material here anyway. There'll be almost no results or tables saying, you know, our method is better than somebody else. I'm not going to go that way at all. And then in the next two lectures, I will cover some fundamental background material that I haven't really covered here. So by creating one slide, it forced me to think, well, what's the thing that I really care about? I don't really care about being Bayesian. That's actually secondary to what I care about. What I really care about is that we should be building machine learning and AI systems that are rational and automatic. Like the places where things go wrong is when they're built in an ad hoc manner by people who try out a couple things and then give up. So a funny aspect of machine learning is that even though we talk about building systems that learn from data automatically, the actual practice of machine learning is mostly somebody has to solve a problem. They've learned about 2 or 3 methods in their, they're really comfortable with 2 or 3 methods in their grad school education or whatever. They try out those methods. They see if one of them works. They pick the one that works the best, and they say, okay, here's my solution. And that's, and they get paid a lot to do that. Because there are very few people who have those skills who know about those methods. But it's still very ad hoc. It's very suboptimal. And really, it would be much more exciting if we had systems that could reason about learning from data at a slightly higher level. So everything I do is centered around this theme of automating machine learning. I'm going to spend the last few minutes of today talking about 3 of these areas, I think. I'm going to talk about probabilistic programming, which is about automating inference. I'm going to talk about the automatic statistician, which is about automating the discovery of models from data. And I'm going to talk about Bayesian optimization, which is about optimization, automating optimization when experiments are expensive. Okay? I'll talk about those 3 things. I've already talked a little bit about Bayesian deep learning. I'll touch a little bit on this. I won't talk about that. I think maybe Max might have talked about similar topics. And depending on how I feel tomorrow, I might talk about Bayesian inference. Could be by popular demand or lack of demand. Okay, so let's launch into this. So automating inference, probabilistic programming. This is one of the things I'm most excited about right now. And what's the problem? The problem is that all this probabilistic modeling stuff sounds fine, but the way it's done is really painful. Okay, so deriving inference algorithms, implementing them, debugging them. No wonder people don't do this. This is really difficult. It could take weeks or months to get right. That's the problem. The solution to this is this idea of having probabilistic programming languages. So there are really 2 parts to this solution. One of them is we need languages for expressing models, okay? And one way of thinking about that, if you're a statistician, you're actually used to expressing models, and the language that you use to express models is equations in a paper. That's what people tend to do. Another language for expressing models that has become very popular at the intersection of statistics and computer science is graphical models. So we're all very familiar with graphical models in papers, and they're a sort of abstract language that just express some aspect of the model, like the conditional independence relationships. But here's another language for expressing models. Let's take computer languages, okay? So a computer language, a computer program can express a model by simply calling random number generators for the random variables. So if I want to have a model that, has some hidden variables, and then has some deterministic function, and then has some observed variables, what I would have is a computer program that draws my hidden variables from some distribution, then some function that computes that deterministic function, and then it computes the probability of the observed variables. So that idea itself is actually a really old idea, and it goes by the name of simulators. So essentially, it's a computer program. A probabilistic program is a simulator that generates data. Okay? It could be a conditional simulator. It could be generating y given x, or it could be an unconditional simulator, which basically just generates y, okay, without giving it an input x. And that simulator calls random number generators every time there is an unknown or random number in the model. So every time there's an unknown or uncertain quantity, I'm going to abolish the term random. But we're going to call the random number generator to represent those distributions. Okay. So the beauty of that is if I take a general purpose computer language, a Turing complete language, then I should be able to express any computable probability distribution with that language. So it's much less restrictive than just being able to write down equations or a graphical model or something like that. I'll talk about this a little bit tomorrow in more detail. If I end up I might talk about graphical models. So that's the first ingredient. That's the probabilistic programming language. Then the really interesting part of it isn't just the ability to express your models, but it's the ability to do inference in those models. So deriving universal inference engines for these languages that do inference over program traces given observed data. So what does that actually mean? Well, what that means in the language of my lecture today is Bayes' rule on computer programs. Okay? So the best example, I think, to think about is the example of computer vision as inverse graphics. Okay? So what's a graphics engine? A graphics engine is a simulator that takes some, representation of objects and illuminations and the poses of these objects and, clouds and smoke and whatever else you want. Takes some representation of that and it renders that into an image. So basically that's the forward direction of the model. And most graphics engines don't have probability distributions in them, but you could imagine taking an awesome graphics engine and saying, I'm going to have a probability distribution over, the number of people and their hair color and the amount of smoke and, the direction of the light and whatever else the choices that this graphics engine is doing. I'm going to have a probability distribution over all of those things, and if I run my graphics engine in the forward direction, I can generate myself a million nice-looking images. Okay? That's running your simulator in the forward direction. That's not the interesting thing, because the interesting thing is, given an actual image, can I do Bayes' rule on that? Can I infer what those random variables should have been conditioned on that image? The conditional probability of every random choice in the graphics engine conditioned on the observed image. And if I can do that for a really realistic graphics engine, I've solved the computer vision problem. Okay? It's of course a computationally hard problem, but this is an idea that's been around for many decades. It's in speech. It's also been around. It's called analysis by synthesis. So the idea was, if you want to understand speech, one way of doing it is figuring out the mapping from, the sounds you're trying to make through the vocal tract into sound waves, and then, and that's the synthesis part, and then you analyze by going backwards that way. That idea has been around for a long time. And the incredible thing is we can actually implement these universal inference engines. It's possible to do this. And there are a whole bunch of examples of this out there, and they fall along a particular spectrum, which is the spectrum of generality versus efficiency. Okay? So some probabilistic programming languages are super general. And what that means is I can actually write down any computable probability distribution in that language using a Turing complete language. So examples of that are, church, Anglican, venture, language that we developed in our group called Turing, web people, even things like probabilistic C. These are completely expressive languages. Okay? But the problem with them is that because they're so expressive, I could write down models for which inference is computationally intractable. So I shouldn't expect that inference will always be efficient. Okay, sorry, I should have probably included Edward as well as one of these languages. I need to keep updating this list of new languages. Then on the other end, we have languages like Bugs, Infer.net, and Stan, which are less expressive but more efficient. Okay, so the class of models you can express is slightly limited, but inference engines are much more efficient for that. And under the hood, the inference engines are things like Metropolis Hastings, variational inference, particle filtering, slice sampling, particle MCMC, and so on. Again, these are things I might talk a little bit about tomorrow if you don't know about them. How many people, incidentally, have used an MCMC method? Pretty good number. How many people have not used an MCMC method? Okay. All right. That just helps me plan my lecture tonight. All right. So this is public programming. Here is an example of hidden Markov model written in our language called Turing, which is based on Julia. And actually, I think I can show maybe a little video of this. It might be more fun. Okay, so this is a hidden Markov model. This is actually all it is. It's hard to imagine. Sorry, it was so fast. Okay, I'm going to stop it. Oh, I didn't stop it. Okay. All right. Okay. There. So this is how you would write down a hidden Markov model. And if you know what a hidden Markov model is, it's basically we have some states which have a categorical distribution, and you draw them. This tilde means draw from a distribution according to some transition matrix, and we have observations that are going to be drawn from some normal distribution with a mean indexed by the state and variance 1. Okay, so very trivial little problem. And basically, this is Julia code. We can write anything in Julia, Julia is a nice scientific programming language, kind of meant to be a replacement for MATLAB, but a much better programming language. You can write any Julia code in here and use these things like tildes to represent some random variables. And then when you want to do inference, you sample from the model. This model is called HMM. And here it says use particle gives with some parameters. Okay. Or we can make those default so people don't even need to know what's happening. And then basically it does some inference, and it's sort of, this is a bit boring, but it's just visualizing that it does inference. It's trying to figure out what these states are, and you know, this is representing samples of these states over time. Now, what we've done here is changed a couple of lines of code, literally these lines of code, to go from a hidden Markov model to a Bayesian hidden Markov model. Okay, so the difference between a hidden Markov model and a Bayesian hidden Markov model is just that our means themselves have some prior distribution, and our rows of our transition matrix are going to be drawn from some other distribution, like a Dirichlet. Okay, so we have Dirichlet's normal, categorical, normal. We can use anything from the distribution package in Julia here, and all of it sort of handles automatic differentiation, forward mode automatic vector, forward mode automatic differentiation, which is kind of interesting. So then, again, we can sample, and here now we're doing a combination of Hamiltonian Monte Carlo and particle Gibbs for sampling. But, you know, it would just take a few minutes to go from the hidden Markov model to the Bayesian hidden Markov model. And the great thing is then we can iterate very quickly over different model choices without having to rederive all of our samplers and things like that. Okay. So the Bayesian hidden Markov model has more uncertainty about where those means are, and so that's why they're jiggling about when you showed the sampler. And it sort of seems to be there. And we validated against other methods like STAND. This is a mixture model. Again, the notation is very straightforward. It's very easy to write these models down. This is how we would write latent Dirichlet allocation in this model. So we have, Dirichlet is the categorical, is the categorical. You just basically write down the model, and then here inference is some combination of Gibbs composed with particle Gibbs and I haven't calling it, and it basically gives the same results as STAND. Okay. So that's the idea of probabilistic programming. Any questions about that? There's some great resources, and actually in my group at Uber, Noah Goodman, actually, who's written a book on probabilistic programming, is also part of Uber AI Labs, and we have a team that's developing a probabilistic programming framework that we're going to use internally for a lot of our modeling methods and problems at scale, and we're also going to release to the world hopefully soon, so as open source software. So questions? Okay, I can repeat your question if you make it short. Okay, it started out with, yeah, go ahead.
But there's a lot more things that you can express in them, like mutual recursion, all kinds of, crazy things that can't write a VM, but which can do inference on. And yeah. I'm just curious where you're coming from.
Yeah, I think, the examples here are actually boring examples because all those examples are familiar graphical models that people know. I think the more exciting examples are if you take something like an existing simulator and you augment it with some aspects of a probabilistic program, like some uncertainty in the inputs of the simulator, like take a physics simulator or a weather simulator or something like that. If that's written in Julia, then we could just do it, or if we can call it from Julia, then we can just do probabilistic programming on that existing system. But also the models like more complicated models like non-parametric models, models that have recursion, probabilistic context-free grammars, things that are maybe not so easy to express as graphical models, we can certainly do like that with these things, and we just need to show more examples of that. But also hybrids of neural networks and probabilistic models. So, variational autoencoders, things like that, are very easy to write in probabilistic programming. So, there's a huge amount of potential. We just need to come up with A, bunch more examples that indicate this, and B, efficient inference algorithms that actually work quite well generally. And we have been doing some internal benchmarking at Uber to see what's actually useful, because we want to be rational. We don't want to just be dogmatic about what we just want to do something useful.
So, this works. It seems like a lot of research at the beginning in probabilistic programming was, hey, I'm going to take a programming language, and I'm going to make a probabilistic programming language. Later it was, hey, this budget some this, I'm going to prove that they're correct in my programming language. But all of that seems to now be dropping off. There's only so much of this one to do. What do you think are the future frontiers in probabilistic programming? Are interesting areas that may perhaps not be explored sufficiently? And what do you think is the next big thing driving probabilistic programming forward?
Yeah, so that's a great question. First of all, I think if you're working on a new inference algorithm, you should always be thinking about probabilistic programming as the target, unless you want to have people rederive it for every different model, which just seems crazy. But in terms of really exciting directions for probabilistic programming itself, the thing that's really missing is a level of intelligence that basically decides what kind of, you're laughing, Dave is my PhD student, so he shouldn't even be allowed to ask questions. He knows what I'm going to say. He's just, yeah, we're doing a kind of public supervision, I guess. But yeah, so actually, I think what we really need is a system where you write down the model, okay, and then there should be some program analysis that can look at that model and identify, parts of that model that can be handled with various inference algorithms, known inference algorithms, and then compose those inference algorithms to sort of automatically figure out a good way of trading off computation and accuracy. So all of that should not be in the human's hands. You should be doing the fun stuff, which is writing down the models, and then the computer should be doing the hard stuff, which is figuring out how to do the inference algorithm, which could be some combination of variational and CMC, optimization, or whatever. Yeah.
So do you not think that probabilistic programming is mainly used to express quantities and problems that are simple enough for a human to be able to figure out exactly what the right inference algorithm is, and that at this stage in the development of probabilistic programming, we really do not need such methods. We are largely playing with toy examples and rarely large-scale problems.
I think that there are a lot of useful things you can do with probabilistic programs on modest-sized data sets. Not all machine learning problems are absolutely vast. So I think already the tools that we have out there are pretty useful for data analysis. I'd like to see, what another vision that I have is that I would love to see, in science, people talk about open data and open publication. But we should be open about our models too. So if you have a scientific paper, it would be very nice if the model were expressed as a probabilistic program, so people could then take that model and evaluate it on new data, let's say, or modify that model to improve science. So those kinds of applications might not necessarily involve huge data sets, and I think that there is a promise of approximate inference methods that are pretty good and scalable. They might not be great. We don't want to go for the holy grail of getting exactly the right Fourier distribution. But if we can do a little better than optimization and represent our uncertainty in these complicated models, I think we're doing quite well. So I think there is a lot of promise for scale. So I'm going to finish probabilistic programming, and I think then it's a good time to stop, and I'll pick up, because this part of this lecture is pretty modular, I'll pick up on, okay, I showed the video, okay, our language is called Turing, and then we can stop here. So I'll take a couple more questions, and then we can move on. That's good.
So I just wanted to go back to the distinction between algorithm and the model. And so it seems that either you're being deliberately cheeky, saying that the agents are part of algorithm, that you write down a model model, then just happens that if you follow the right laws of probability, then the equation is like the only type. Or maybe the prior is part of the process, algorithm choice. So when you're showing that you have HMM and then Bayesian HMM, they same model, then same. And if that's the case, then is the choice of prior a matter of cross validation even, or even if it's functional for much of the time? Just,
Yeah, that's a good question. So I don't think of the prior. I think the prior is part of the model. I actually don't like the word. I don't like the word random. I also don't like the word prior. It's all part of the model. Okay. So basically, for me, a model is under-specified unless it can actually produce the data that you said it's modeling. Now, it doesn't mean you have to do a full generative model of everything. And just to be clear, I'm perfectly happy with saying that a Gaussian process, for example, is a model, is a conditional model of y given x. I'm not modeling x. Okay, I'm just modeling y given x. A neural network is a model, except that you haven't, unless you say what the prior over the parameters is not a fully specified model, because I can't tell you before observing the data what the distribution of y given x is. Once you take a neural network and you specify the architecture, and either you fix the parameters, like you say, it is AlexNet, so this parameter is 2.7394. That's fine. That's a well-specified model. You fixed all the parameters, or you have good distributions in all the parameters. Then it becomes a well-specified model. So the prior is part of the model, and you know, in a sense, some models that are out there, I think, are not well-specified models. For example, you know. Yeah, almost every classical model, you don't put a prior on the parameters. So in my mind, it's sort of an underspecified model. It's a little bit like you buy a car, but people didn't put the wheels on, so you have to go and put the wheels on and say, okay, now it's finally a car. Okay. So logistic regression, for example, is not a model until you actually tell me, because it's really a fundamentally different model. If I say I have logistic regression, but I'm going to assume my coefficients, my parameters, range between -1 and 1, that's actually a very different model than saying I have logistic regression, but my coefficients are going to range between -100 and 100. Those make different predictions about the class probabilities given the inputs. So they're all models. There's some that are under-specified and some that are fully specified.
So I have two questions, but they are more or less connected. The first is, 4 years ago when I attended my first summer school, when you were giving the talk about machine learning and all this stuff, there was no mention of neural networks at the time. So basically your talk started almost halfway through what you talked about today. So it seems like the landscape of machine learning is changing, and somehow people are learning machine learning differently. At the same time, when I was learning about probabilistic programming, for example, they were also methods to have probabilistic inference as part of a program that you write for different applications. And at the time, I remember Infernote.net was very, very popular. And then later on, people were talking about probabilistic programming in the context of just having an easy, something like TensorFlow that people use today, which is an easy way to specify models. Now it seems like probabilistic programming is becoming different. So which is it? What is machine learning? What is probabilistic programming? Is it always going to be changing?
It's hard to predict, right? Certainly, I will agree that the landscape is very different now than it was 4 years ago. There was a reason for that. I mean, neural networks have been very, very successful. In terms of what probabilistic programming is, I would like it to be as easy to use as PyTorch or something like that. Easier than TensorFlow, let's say. You know, what the problem is, it will never be maybe that. Well, no, I think there's a lot of kind of just sharing of knowledge. I mean, these neural net architectures are pretty crazy weird, right, these days, and people kind of accept that. So they will, you know, at some point they might accept like modules that are bits of probabilistic models that they can compose together to put together other probabilistic models. The nice thing is the interface is very analogous, right? In kind of differentiable, you know, end-to-end systems, the interface is you have to be able to pass derivatives, right? Whereas in probabilistic programs, the inference is you glue things together with probability distributions. And maybe you want to pass derivatives as well. Right? So it's, I would like it to be as easy to use as the sort of main software frameworks for machine learning in deep learning. I also think, watch this space, I think we will soon have systems that are complete hybrids of the two, where you can do deep learning or probabilistic modeling, and anything in between, right? Any mix and match. That would be ideal. There'll still be a lot of other problems in machine learning to worry about. So, you know, the field will keep changing, I'm sure.
I have a question regarding Bayesian neural networks and your statement that they will help us to get better uncertainty estimates and understand better what the model learns and what the model doesn't learn. Specifically asking about the prior, because earlier you had a very strong prior that there wouldn't be more than 90 people in this room. And if you use this kind of prior to make uncertainty predictions, they will probably also not be quite as accurate as you would want them to be.
Yeah, so it's certainly true that if you make poor assumptions, your uncertainty estimates will be poor, and your predictions will be poor. Actually, worse. You know, it's worse if even your predictions are bad than, you know, without worrying about whether your estimates are good or bad. And so we do need to be careful about our priors. But I think there is an issue with people being overly careful and saying, well, I'm not going to use Bayesian methods at all because I don't want to have prior, so I'm then therefore not going to have any, you know, even attempt to have calibrated uncertainties. So that will, I might talk about that tomorrow. So I might talk about like how do you choose priors. But, you know, the sort of punchline there is there isn't a single correct way of choosing priors. It's not like there's a wrong prior and, you know, a right prior and a wrong prior. There are representations of uncertainty that correspond to different models. Just like, you know, there isn't a right car, right? You know, there are many different cars you could drive out there, right? There are different models, right? They all things like that you may The bigger issue is how do you identify when your model went terribly wrong? This is a very nice area where you can marry classical statistics, classical frequency statistics, with Bayesian statistics. So you could do your modeling from a Bayesian perspective, and then you could say, well, are there any aspects of the data that are statistically significantly different between what my model says and what the data is. So you could do classical kind of two-sample tests or hypothesis tests to see whether your model can be falsified or not. So this is a nice place to marry the two frameworks. And cross-validation, by the way, is not a Bayesian framework, but any sensible person will do that. Hold out some data and evaluate on that held-out data. That's a reasonable thing to do, although it doesn't follow from the sum rule in the thought. You should condition on all your data is one of the aspects of Bayesian. That part we will ignore safely. Maybe I should take the last question because we are pretty over time. Yeah. But
Yeah, so besides the inference engine and probabilistic programming, do you think there will be also capacity for causal losses or something like that? Because I see the need for the inference engine, but beyond that.
Yeah, I think that so probabilistic programs can be used to represent causal processes. They can also be used to represent things that are totally not causal. So in a sense, it's a little bit orthogonal. The probabilistic programs are directed, but almost every kind of sensible framework for thinking about probabilistic programs involves a generalization of directed graphs. So basically, you execute the program from top to bottom, and that's like ancestral sampling in a directed graphical model. So in that sense, because they're directed, it's kind of natural to be able to represent causal relationships. The more interesting question is, can we use probabilistic programs to infer causality from observational data, or to make decisions about experiments to do to infer causal explanations? And I think like any probabilistic tool, they can be used for that, but they're not going to be the whole answer. So it's sort of, we need more theory, we need more understanding of causal inference combined with probabilistic model. Okay, I should probably stop there. It's pretty late, and I will pick up again tomorrow. And if you have any special requests, send me an email. Yeah.